notes. If you want to flip to that picture in your notes, I just want to add one little thing to it. When we were talking, we said this was a minimum, and then you guys were like, whoa, but there's two minimums. And then I said this was the global minimum. And then I think someone asked if this would be the global max. And I'm not sure if I gave the best answer, but I just want to clarify. This would not be a global max. It would just be called the max, or maxima. And the reason is that we have other y's going up over here and over here that are higher y's than that one, and so we can't call that a global max. I just want to clarify that in your notes from what we took last week. So add that on or cross off global if you did have that there. Okay, good on that? Next, go to the interval. We took some notes about intervals. We did 5 of them. We're actually going to add 2 more to that list. So this is where we have the thirds. So we have the graph and then the notations. So you had interval notation next and then set notation. Interval. If you have space at the end of your list, go ahead and add it to the bottom of that list. Notation. Set notation. Okay, so we're just going to add on 2 more of those. What if we have a situation where, so we had just A and B in our little number line graphs before. What if we have an open A shaded to the left at A. We have filled in B that goes to and stops at an open C. I'm going to copy that down so you're writing in your notes. You have a number line graph A, B, C. A is an open circle shade to the left. Shade between B and C. B is closed, C is open.
What's the name of these one?
It's kind of like a combination of some of the other ones. It's an open infinite set with a half open interval.
Can you write it?
Yeah, so this part would be open infinite interval. With half open interval. With half open. Half open interval. And interval notation we've got from negative infinity up to A, but we can't equal A, so we use a parenthesis. Union with B, we can equal B, so it's a bracket, to C, parenthesis and C, because we cannot equal C. And we're just going to skip set notation on that. Okay, one more example. A, B, and C. Solid A, B and C are open, and we're shading between all of them. Solid A, open B and C, shade between all of them. And this is you can equal A, so that's a bracket there. We're going from A to B, but you cannot equal B, so it's a parenthesis. Union, we're joining it with, again, B, but can't equal it, just a parenthesis, between B and C, so B comma C cannot equal C, so parenthesis, and that encompasses our points. Okay. Just want to get those in there. We're going to skip the set notation for those for now. Okay. Next, and this is for everybody. This is you guys too. So parent function. So this is a new section or a new topic. Are you good on this? I can erase.
I just need the bottom one.
Bottom one. Okay. So this will be a new kind of topic. Maybe you want to flip to a new space. You'll be using a lot of space for this. We're going to call this one parent functions. Parent functions. Okay. All right, and we're just going to give ourselves like a loose sketch of what these look like. So, if you need the last notes, just get that from a partner at this time. So, first one, we're just going to start with the most basic, linear, and this is when your y equals f or x, or your function. Remember back we started to say, well, what if you replace that y with this fancy f and an x thing, and I want you to think of it as the y. So that's what we're going to do in this class. You're going to think of that y as an f of x now. So linear, marker. Just that straight line, one-to-one correspondence through 0. And of course we can, put numbers in front of x or add on to x, or we can make negatives, right? And that'll shift that line, left, right, up, down, change the angle. But this is the parent function, okay? Quadratic. Think of it as f of x equals x squared. Again, we can add a bunch of different things to that equation. Plus or minus things, multiply things on, throw some negatives in there. We can change it, but the parent is a U shape that hits at 0, 0. That parabola shape, that's our quadratic.
Oh, I hate parabolas. Wish you were less vocal with your opinions.
Okay, here's another one, cubic.
Yeah.
Cubic, C-U-B-I-C. We notice a pattern with our x's. This is x to the 1, this is x to the 2. What do you think this one's going to be? X to the 3. Okay. Kind of looks like that. It's kind of like an S, sideways S, and it goes through 0, 0. Now there's other ways you can do this if you want to put a reminder for yourself. So the parent function of cubic, it really doesn't look like it has a min and max there. It just kind of goes straight through 0, 0. But a lot of times when you see a cubic example, it'll have a more extreme kind of sideways S where there's a very clear 1 max and 1 min. But sometimes cubic, they look kind of straightish, but these are both examples of a cubic function. Questions? Okay, so it might be helpful to try both of those. Let's do absolute value. Absolute value function. Anyone remember what this looks like from algebra 2?
A V.
Yeah, a V, and for the parent function, the vertex of that is at 0, 0. Yeah. Absolute value, which would look like black. Sorry. F of x equals those big absolute value bars around the function. Okay? Again, of course, we can add numbers, subtract numbers, we can multiply this by numbers, we can throw in some negatives, and it'll change it. It'll flip it or shift it all around, but this is just the parent function, so you recognize the shape. Yes, sir?
For the two lines, are they like the same angle as the linear one?
Yeah, this one. Yeah, it's like taking, so these stay the same, and these negative ones get flipped to positive ones up there. Yep. So, like a transformation of the linear function. All right. Reciprocal.
Oh, here.
Reciprocal function. So we're taking 1 over x would be the reciprocal. So function of 1 over x. And you get this like kind of shape like that. It's supposed to be. Like they kind of approach the axes. Okay, we're copying this in our notes. Okay. Liam, you have a question for us?
No,
Okay.
not usually.
Next one, let's write it down. Exponential. Exponential.
Growth?
Yeah, that's an example, but we could also have exponential what?
Decay.
You got it.
It's exponential decay. Exponential growth.
This doesn't actually pass through 0, 0 in the parent function, but on the left side it kind of approaches 0 and it goes up like that.
That looks a whole lot like quadratic. What's the difference?
What's the difference? So these are both going to be going up towards infinity. This one, the right half, yeah, it kind of looks like quadratic, but this one
Not the line.
is actually.
The equation, the exact.
Oh, did I write it wrong?
Maybe.
Oh, yeah, I did. Good call. E to the x. Sorry, I wrote it wrong. E to the x. Good call. Sorry about that. Go ahead and change. E to the x.
Of course, yes.
Okay.
James, you need to be as smart as me, you don't understand.
All right. If you still need linear or quadratic, go ahead and get those from here. Logarithmic. So when you guys see a problem and you see you can identify what that equation, like that base of that equation is or what that part is, you can glance at this image and say, oh, that's what I should be getting as a general image. So logarithmic function will do f of x, let's do a natural log ln of x.
Logarithmic.
So that would be.
Yeah, this was toward the end of the last year.
Yeah, in the last year.
Advanced algebra.
Okay, rough sketch.
What's the thing after the f of x?
An L, like a cursive L,
Okay.
and a italicized, or like an italicized L and an N. It's LN. It's LN, but make them kind of, fancier.
I think I enjoyed those. I am reductions.
Next, we have the square root. Square root parent function f of x equals the square root of x. And this goes like that. Square root function. Curves and then goes pretty straight. Okay, maybe I made that too drastic, but just like curve and go straight. All right, sine and cosine you should always be able to recognize as a big squiggly going on and on forever. And there's one cool detail to differentiate them. So let's do sine first. So f of x, sine of x. Again, you can still throw numbers in there, multiply numbers on, add some numbers, throw in some negatives. It'll change it, but this is what the original looks like. So when I say squiggles, I mean like this, right? Forever and ever. So with sine, you pass through 0, 0, and with cosine, you don't pass through 0, 0. So this will be, it starts, you're going to do a squiggle, squiggle, but make sure it's going through 0, 0, and it is like a linear start, positive, positive, negative, negative, and then it's just a bunch of squiggles. Like that. We're almost done. 2 more. So cosine, very similar. So now it's the same shape, but the peak of one of these crests is actually going to be what's on the y-axis, so we do not go through 0, 0. So it's the peak of one of those zigzag things. They're supposed to be uniform. Those aren't perfect, but
It's probably the same as the sine x with cosine of x.
Bless you.
But I see you're using a pen, so you can't afford to get it wrong.
What's the equation?
oh, yep, equation, good call. F of x equals cosine cos on the calculator button. Cosine x. Okay,
Bless you.
get both of these down. We got one more.
It's sunny.
I thought you hated sunshine. I thought you were sick and tired of sunshine.
Well, I like winter, but I also like grass.
So it is the tangent, T-A-N-G-E-N-T, which will be f of x equals tan is the button on the calculator, T-A-N of x. And it looks like this one passes through 0, 0, and you get kind of like the cubic, but you get a pattern. So the cubic one kind of looked like this, but these are going to be really narrow, and you do a bunch of them repeated. So like where it crosses, where that shape changes should be where you're passing the x-axis.
And the lines will never like go under each other, right?
Yeah, there should always be, that's not the right next example. They shouldn't overlap, right? That one's a bad one. Like I'll never
Too late.
tuck underneath of another one where they have the same x's. That won't ever happen. We're far enough away that they all have a different x the whole time. And over to this side too. That's not really far enough. All right. That's tangent, tan x. We're done. Questions on those so far?
Wait, what's the difference between sine and cosine?
Where where they hit. So this one, sine passes through 0, 0 at that kind of linear line pattern is how it crosses.
Okay.
And I say that as opposed to going through that way. For cosine, it's the peak, the crest of one of them hits on the y-axis.
Okay.
That would be the difference. That'd be a good note for you too, just to circle those 2 points, because maybe you look at these notes far in the future and you forgot the difference. Maybe just circle. That'll be a good reminder for you.